This is the fifth lecture of our IMAT series chemistry. Today we are studying transition metals elements. Okay, here some overview of the periodic table. Where, rows are periods, columns are groups. This is halogens. There are noble gases, alkaline metals, these are alkali metals, and here we have transition metals. Okay, D block elements or transition elements are so called because of their position in the periodic table. Their properties are transition between S block elements from ionic compounds and P block elements, largely covalent. You can see here these are like in D D block. Yeah, these are block. S block here. This is S block. This is P block. This is D block. Okay, and there's F block as well. There are a total of 18 groups in 4 blocks. Each block contains a number of groups equal to the number of electrons that can occupy that subshell. DNF blocks, the D block consists of 10 groups, 1b to 8b, or from 3 to 12, and known as main transition metals. The F block of the periodic table of the element consists of 14 groups and are known as inner transition elements or lanthanides or actinides. These are all our transition metals. D block elements is and inner transition metals F block. Okay, we are only like study these topics in deep. Not all D block elements are transition metals. IUPAC defines transition element as an element that has an incomplete d-subshell in either the neutral atom or its sign. Okay. Importance of transition metals. Play a role in organisms alive, such as iron, copper, chromium, nickel. Human body contains iron, copper, many of these substances. Okay, and production of various materials using chemical processes involves catalysts. Iron is used as a catalyst as well. In order to understand also transition elements in biological systems or chemicals involving them, it is essential to understand the principle underlying the chemistry of these elements. These are like overview of cadmium, titanium, vanadium, chromium, cobalt, nickel. Okay. Representative elements. Chemistry changes across periods. Similarities occurs within a group. Transition metals similarities occurs within a period as well as within a group. Okay, due to last electrons being d or f orbital electron, d and f electrons cannot easily participate in bonding, so chemistry of transition elements are not affected by increased number of these electrons. For series 3 we will study only 3D series more deeply. 4D series, 5D series, 6D series. Okay. Properties of transition elements. They have very similar physical and chemical properties. Metals with high boiling point, melting point, and high density. Most have multiple oxidation state. Their most common oxidation state is +2. Many of their compounds are colored. They exhibit interesting magnetic properties. They form metallic complexes, coordination compounds, complex signs, and organometallic compounds. Can use orbitals from two different subshells for bonding, 4s and 3d. Many of the metals and their compounds are good catalysts. Okay. General properties of transition elements. Densities of transition element increase with the increase of atomic number due to increase of atomic masses, while the atomic radius is nearly constant. Metallic melting and boiling point. The elements of the first transition series have high melting and boiling points because they have strong metallic bond resulting from sharing of both the 4s and 3d electrons. 4s and 3d electrons. The metal melting points and the molar enthalpies of fusion are both high in comparison to main group elements. This arises from a strong metallic bonding in transition metals, which occurs due to delocalization of electrons facilitated by the availability of both d and s electrons. Okay, so they have high melting and boiling points. General electronic configurations of the elements. First series have this 4s 1 or 2 and 3d 1 to 10. Okay, the transition metal from ions to the loss of ns electron before the n-1 d electrons. The definition of transition metal excludes zinc, cadmium, and Hg. They are represented by the general formula n-1 d10 ns2. These orbitals in these are completely filled in the ground state as well as in their common oxidation state. Therefore, they are not regarded as transition elements. They show some properties like they are non-typical as transition elements. You can say. Electronic configurations. We studied these principles in our previous lectures. Of principle, fill up electron in lowest energy orbitals. Pauli's exclusion rule: no two electrons in an atom can have the same set of four quantum numbers. Hund rules for degenerate orbitals: the lowest energy is attained when the number of electrons with the same spin is maximized. This is order of filling of electron: 1s, 2s, 2p, 3s, 3p, 4s. This is the order. Okay, electronic configuration. Okay, of like potassium here, like 4s, R1 and 4s1. These are scandium transition metals. Okay, scandium, titanium, vanadium, chromium. These are like electronic configuration of these elements. Manganese, iron, cobalt, nickel, copper, and zinc. Okay, here electronic configuration of all these elements. Okay, yeah. Many factors affecting the filling of N minus 1D and NS sublevels. Like in chromium, you can see we have to do this, but the correct configuration is 3 4s1 3d5. Okay, both 4s and 3d becomes half filled. It okay, for copper as well. This is not correct. We write 4s1 and 3d10. D orbit is completely filled and 4s is half filled. These are exceptions. Okay, like you can say we follow this rule, Hund's rule. Okay, ions. Transition metals are defined as metallic elements with an incomplete d-subshell in at least one of their ions. From positive ions by losing electrons. If you can see here, iron loses 2 electrons. Okay, here explain why iron 2 is easily oxidized to iron 3 while manganese 2 is not easily oxidized to manganese 3. Yeah, here's the answer. The electronic coefficient of iron is this: 4s2 4d. Yeah, 4s2 3d6 here. Sorry, 3d 3d. This is 3. Okay, 3 here as well. 3 here. Okay, when we lose 2 electrons of iron, we have like 4d6 left. You can 3d6 left. So when we lose another it is partially filled, so it is easy to remove another electron from Fe2 positive, and it becomes 3d5. While when we lose 2 electrons from manganese, it becomes 3d5. It is half filled and more stable. So it is more stable. So we will face difficulties in removing electron. Okay, and this is less stable, so it prefers this. Abnormal exceptions of electronic configurations: chromium and copper. The transition elements of the first series gives plus 2 oxidation state, because when they gain energy they will lose 2 electrons from the sub-level 4s at first. Scandium cannot give oxidation state plus 2, but it gives oxidation state plus 3, because when the atom gains energy it loses 2 electrons from the sub-level 4s, then 1 electron from 3 tablet to be more stable. Okay, that's why it gives plus 3. Transition elements are characterized by having variable oxidation states. Okay, because of the two sublevels 4s and 3d of really equal energy, and the electrons are lost in sequence when the atom is oxidized. You cannot give oxidation plus 4 state. Okay, because the amount of energy needed to obtain this ion is greater due to breaking of a complete energy level. Because, okay, you can see its electronic configuration. Oxidation states, you can see here. Manganese show more oxidation states: plus 2, plus 3, plus 4, plus 5, plus 6, and plus 7. Oxidation states. Okay, plus 2 is the more common state. Ionization energy values. Okay, ionization energy across rows increases. Third transition row has higher ionization energy than the first two rows. Higher oxidation states are more accessible to third row metals. Variation atomic volumes, you can see here. Atomic volumes, yeah, these are like same. It like decreases. Transition metal volumes decreases from left to right across the period until the near end the size increases slightly. You can see here, slightly increases little bit. Here decreases and increases little bit. Atomic size are expected to increase down all the groups in the periodic table as additional stellar electrons are added with increasing atomic masses. Okay, atomic sizes across period R decreases, down a group R increases. This is activity. Magnetic properties, we take honeycomb, most main groups honeycombs are colorless and diamagnetic because the metal line has no unpaired electrons. Calcium metals and D0 or D10 are also colorless and are diamagnetic. Many transitional metal ions are highly colored and paramagnetic because the neutral atom of one of their metal ions has one or more pair electrons, so they show color compounds. Okay. Yeah. Magnetic properties. Transition elements are paramagnetic due to presence of unpaired electrons in the d orbitals. You can see definitions: unpaired electrons and no unpaired electrons. Okay. Here are some examples as well. Yeah. Good. Here are some questions. Here, Z and Cu2 per CFC. We write the order of momentum of these elements. Number of unpaired electron, diamagnetics. These are pop. These are all the answers. Okay. Yeah, these are the answers. Okay. The colors. Atoms or ions of transition elements are colored due to presence of unpaired electrons in the orbitals of d sublevel. The color that is not observed by substances, you can read here, complementary observed colors, transition metals in colors. The colors of d-block metals are a characteristic feature of species with the ground state electrons d0 and d10 are often highly colored. Okay, these are some compounds: chromium, manganese, cobalt, and they show some colors here: sky blue, pink, intense purple, dark purple, blue. Okay, in contrast, salts of SA and are colorless because they have no unpaired electrons. Yeah, DD transition help in colors. Okay. Okay. Properties: chemical reactivity with oxygen, some form oxides that adhere to the metal, protecting the metal from further corrosion such as chromium, nickel, and cobalt. Some form oxides that scale out, resulting exposure metal to further corrosion, that is iron form oxide with oxygen to prevent metal from corrosion. Some noble metals do not form oxides easily. This is silver, gold, platinum, okay, palladium, forming ionic compounds. Transition metals form more than one oxidation state. Complex ions formed by a cation is surrounded by a certain number of ligands. Most compounds are colored. Transition metal ions are observed visible light. Transition metal ions contain unpaired electrons. Catalytic properties: they are used as catalysts that increase the rate of reaction without being consumed. Okay. Homogeneous catalyst: single phase hydrogen multiple phase reaction as well as in enzyme catalyst. Most transition metals and compounds have good catalytic properties. There is variable oxidation state. This is the reason why they have good catalyst. Variable oxidation state provides large surface area for the reactant to be absorbed, not absorbed, absorbed. Some typical reaction, like you can see Haber's process here, iron is used, contact process. Okay, hydrogenation, decomposition, catalytic converters. Okay, these are double salts. They, they are role in double salt and coordination compounds. You can see here. Okay, okay, okay. Complex compound, complex compound. You can see here. Complex compounds are species class of compound if the metal atoms or ions are bound to member of anions or neutral molecules. Okay, this is for the today topic. I hope you like the video. If any confusions in today's topic, let me know. I will help you out about the, like, you can say, details. Also try to link binding energies as well. You can, the number of unpaired electrons increases binding energy. You can more number of unpaired electrons, more binding energy. Okay. Uh, Try to revise previous lectures as well, to get better understanding of these topics. Thank you so much.